So, and typically the devices are connected in an open collector mode in the network, which means you need to have pull up resistors to maintain the static logic level of the network. The wiring involves two lines, one is called the serial data line or SDA line, and the other one is the serial clock line or SCL line. So, regarding the design, I will come a little later. The I2C clock is not a traditional clock. So, it is normally kept high during a pull up. So, when we are having just like the SPI, this I2C is also a synchronous communication protocol, which means that the transmitter and the receiver should agree on a common clock signal. So, there is no notion of store and forward or buffered transmission and reception of data. Data is basically transferred along with the clock signal, as in case of SPI. So, since we are using a pull up resistors, the normal voltage level of the lines is kept at logic high, and then a high to low transition in the SDA line or system data line basically indicates that a data transmission process is getting initiated. Similarly, at the end, when you have a low to high transition, it indicates that the data transmission process is stopping. So, it is pulsed by the masters during transmission. Master can either be a transmitter or receiver. Is it okay to say that the master can either be a transmitter or the receiver? Huh? It is? It is with respect to data. Transmission and reception is with respect to data. So, if it is receiving the data, can it be called master? Yes or no? No. Yeah, master is the device which issues the control signals. So, irrespective of whether it is transmitting data or receiving data, we have to see the device which is actually transmitting the control signals to control other devices on the network. So, that is why we call it the master. Now, if it is transmitting the data also along with the control signals, then it is said to be in the write mode. If it is receiving data while sending control signals, it is said to be in the read mode. So, naturally, master could be either transmitter or receiver. Slave device can hold clock low if it needs more time, which basically allows for the facilities for flow control. Huh? So, there has to be a time division multiplexing mechanism. First of all, one of the biggest issue with a single master receiving from multiple slaves is that the speed of the master should be manifold compared to that of the slaves. It depends upon number of slaves the master is reading from. Now, as you are sampling the data from the different slaves, they have to be multiplexed using a time division multiplexing mechanism and then passed on to the master. So, if you have n number of slaves like this, and then the master is like this, then suppose this is the master's clock, then at this pulse it should read this slave, at this pulse it should read this slave, and so on. So, it may take place in a round robin fashion or based on some chosen priority based mechanism. So, when you have the notion of multiple devices talking to each other or multiple devices talking to one device on the network, the notion of multiplexing has to be there. Otherwise, you have to use dedicated communication link for each point to point link on the network. So, if you have enough money, then you can have this kind of a mesh network So, you will end up sending only the data and no address information, because when this device wants to talk to this device, it will use this line only, which will not be used for any other communication in the network. Similarly, when this device wants to talk to this device, it will use this line only, and this line will not be used for any other communication on the network. Huh? 6, no, over here I am using, suppose I want to connect say 10 devices of the network. So, in that case you need to have 10 C2 lines on the network, right. What is this 10 C2? That is 45, you need 45 lines on the network. Now, if you have enough money to fund for those 45 lines, then it is fine. Otherwise, if you feel that you are poor enough not to be able to fund for it, then you have to think of these multiplexing mechanisms. Unfortunately, we are in a poor country with lots of constraints. So, our priorities are on a different basis. There is no notion of master slave at all in a mesh network. The notion of master slave comes up with respect to which device is controlling the transmission, which device is controlling the reception, that's or which device is controlling reception, that way. So, for this kind of a network, any device can act as a master or a slave depending upon the requirement. So, the transmitter receiver, as I said, that it differs from the master slave notion. Normally, we have a perception that master is the transmitter, slave is the receiver. It is not the correct way to think. The correct way to think is the device that initiates the communication or the transaction is called the master, and the slave has to respond to it. So, the transmitter sets data on the system data line and the slave acknowledges. For a read, slave is the transmitter, master is the receiver, and for a write operation, master is the transmitter and slave is the receiver. So, if you now see the I2C connections, then a single device, this PIC microcontroller is connected to multiple devices on this bus. So, each device has got two pins, the SCL and the SDA pin. So, through SCL the clock information is being transmitted, through SDA pin the data information is being transmitted or received. Now, in order to suppose this device wants to communicate to these three devices on the network, then it also need to have the address information. So, for that you need to have the address bits. So, you can customize these address bits by keeping something someone at logic 0, someone at logic 1. So, likewise you can have 8 such devices connected in the network, so that it will have addresses ranging from 000 to 111. Now, if you see the address format, it has got first 4 bits are basically encoded within the device and cannot be changed. The next 3 bits you can change according to the way you connect these 3 lines A2, A1, A0, and the last bit basically indicates a read or a write operation. If it is 0, then it is write mode. So, the data is transferred from the masters to slave. If it is 1, it is read mode, the data is transferred from slave to master. Okay. Do you follow it? Why do we need to use? Yeah. So, normally the chosen protocol is the resting potential of the line should be at logic high, and when there is a low transition, it indicates when the master gives a high to low transition, then it indicates that the device intends to send some data. So, the falling edge is detected as the initiation or start of the process. So, when you want to start the data transmission process, the master pulls the SDA line low while SCL is high. So, this is an exceptional case, because normally, as we will see, the SDA changes only when SCL is low. So, when SCL is high, you are actually sampling the data, that is called the sampling interval, and when SCL is at logic low, then the data is allowed to change, which means it is the data change interval. But in case of the start condition, the SDA goes low when the SCL is high, which creates the exception, indicating that the device wants to communicate. So, unlike other cases where you have data line going from high to low or low to high only when the SCL is at logic low, in this case the SCL has got a high to low transition when SDA goes from high to low, that is high to low transition when SCL is high. the data is always sampled on the rising edge of the clock signal. The address is 7 bits, which means that you can connect 2 to the power 7 devices on the network, which is a good number to deal with. And 8 bit indicates read or write operation. It is high for read, low for write. These addresses are assigned by Philips or NXP Semiconductors for a fee. It was covered by patent. Now, if you see the data transmission, the data is transmitted just like address. So, for a write, the master transmits, the slave acknowledges. Now, if you see, when the clock is at logic low, then only you have the interchange of data taking place, as I told earlier. So, when the clock SCL is at logic low, then and only then you can see that this interchange of data taking place. And on the rising edge of the clock signal, you sample the data, or in sometimes we also sample the data sometimes when the clock is at logic high. So, once you create the start condition, you can keep on sending, and once you have sent the address information and being acknowledged by the slave, you keep on sending the data bytes one by one in this way until the master creates the stop condition. So, the master is the device which initiates the communication as well as terminates the communication, and slave is the device which basically acknowledges the initiation of communication and termination of communication. So, if you see the I2C stop condition, then the master pulls the SDA line to logic high while the SCL is high. So, this is just the opposite of this initiation of communication condition or start condition. When you had SDA going from high to low while SCL is high, over here SDA is going from low to high while SCL is high. So, any such data transition taking place when the clock is at logic high, it indicates initiation or termination of communication. So, now if you see the actual communication taking place over here, you can see that this high to low transition actually initiates the communication, and then you transmit the address information first, followed by the data bytes. So, when you are transmitting the data bytes, you are typically transmitting from most significant bit to least significant bit, and then when the slave receives them, it also sends an acknowledgement pulse which indicates that the faithful reception of the data. So, the first 8 bits are basically driven by the transmitter, the 9th bit is actually driven by the receiver. So, in a single chunk 9 bits are typically there, of which the first 8 bits are the data bit, the 9th bit is basically the acknowledgement bit, which indicates which is indicated by the receiver to indicate that the data has been received. Yes. Huh? No, the data is always changed when the clock is at logic low.